Right, okay. This really is a weird microphone. Um, okay, thanks everyone. I wanted to also say a big thank you for all the nice feedback, especially about the first few slides at the beginning of yesterday's talk. No, I really appreciate it, and I think it's important actually, which is why I put it in. I was reminded last night, I'm hesitating to say this because this guy was a bit of a jerk, but one of the talks I listen to a lot when I get into a rut, and I get into a rut quite often, meaning I get stuck or I get nervous or feel like an imposter, is a commencement speech at Stanford by Steve Jobs in 2005. I don't know how many of you have heard it, but it's an amazing speech. Just about life choices. It's about how he dropped out of university and never finished, and so he's giving this speech to the graduates but never graduated, and 3 stories on joining the dots, love and loss, and death. And the last one is obviously the most poignant because we know what happened after. And the theme is basically along the lines of if I knew today was my last day, would I want to do what I'm about to do? And as he says, if you have that attitude every day, sooner or later you will be right, which is kind of brutal, but I think he's right. It's a really useful tool for focusing on whether you're doing what you really want to do. So I recommend that very highly, actually. It's a really great speech. Okay, today we're going to talk about mesoscale dynamics. So I forgot to mention yesterday this lovely picture from the Southern Ocean State Estimate, Matt Maslow's. But you can see the Southern Ocean is full of eddies. So I was tasked with talking about mesoscale dynamics, eddy dynamics. And I'm going to start by trying to strip back mesoscale dynamics to the key basics without focusing especially on the Southern Ocean. And then the second half we'll talk about the Southern Ocean. Okay. Right, to start, and any students who were in Bad Honnef last year, or Andrew, or other people who have seen this before, are banned from answering this question, so be discreet. I've got a question for you, in fact 2 questions for you. How many eddies are in each panel? Maybe we can just shout it out. How many eddies are in so it's a doubly periodic domain, I should say, it's a model. How many eddies in the left panel here? 2. How many eddies in the right-hand panel? Anyone? Other than young Matt? 2. Oh, very good. You know it's 2. Ah! Damn it, you're meant to say 15 or something. The answer is this is the same flow field. So 1 is the stream function. Whoa. What's going on with my slide? 1. What? So the left-hand panel is the stream function, so the contours of the flow, and the second is the Laplacian of the stream function, the vorticity. And the reason I show this is your perspective on what's an eddy might vary depending on the field that you're looking at. These are exactly the same flow fields. Right, question 2, a wonderful question that was posed by Ryan Abernathy in a paper. So is eddy a noun or an adjective? I love this question. So I won't get you to talk about it, but the answer is both, I think. So the panel I had on the left-hand side, we're probably thinking more about eddy in the noun sense as a sort of coherent, well, it's not a coherent vortice actually, but some circulation pattern. So you might call this an eddy. Whereas on the right-hand panel where you see the vorticity field and you see all these beautiful narrow filaments, you're probably thinking of eddy more in the adjective sense of an eddy flux of something. And I think this is important, actually, because, again, the literature switches interchangeably between the 2 terms, and both certainly have their place and are important. So eddies in the noun sense are important in the ocean, and there's a couple of examples I've got on slides. One is Agulhas eddies, which is a Southern Ocean example, and this is basically a western boundary current down the Indian continent coast, the Agulhas current, which runs out a coastline and then retroflects to join the circumpolar current, and you shed these coherent eddies. And you can track them into the South Atlantic. So that's one example, and these are important in terms of their transports, without question, for the overall, for example, the salt budget of the Atlantic. And another beautiful example of a subsurface trapped eddy are these meddies that are formed by the shed as the Mediterranean undercurrent. So you have the dense water coming out, the salty water coming out of the Mediterranean, and then going around Cape St. Vincent, and again a retroflection, and you shed off these subsurface meddies, these very warm, salty eddies. So I put those up front because I am not going to talk about eddies in the noun sense in this talk beyond here, but I want to make clear they do exist, and they are important. I'm also not going to talk about the sub-mesoscale. This is a beautiful picture from Jonathan Gula's group of vorticity in the North Atlantic in a model run at 1 kilometer resolution. And if we zoom in on the Gulf Stream region, you can just see this amazing richness of behavior. So I know that Seb was on the agenda to talk about sub-mesoscale, which is great because I don't know much about the sub-mesoscale and I can keep away from it. But yeah, well, I'm not sure many people know much about the sub-mesoscale, really. This is the frontier, very much. Bizarrely, what we call mesoscale oceanography is called synoptic scale meteorology in the atmosphere, and this is the sub-mesoscale is known as the mesoscale in the atmosphere, and that's kind of weird. And I guess the microscale is then the meteorology is equivalent to the stuff we've yet to really get into, the ultra-small scales. Well, actually, people do it already. Okay, so whenever you look at finer scales, the ocean has this amazing richness of structure, but we're not going to talk about the sub-mesoscale today. Right, I'm going to be brave and hope my slide advancer is not going to blip on me again. Right, classical theory. So the classical explanation for why we have eddies in the ocean is baroclinic instability. There are other ways of forcing eddies. You can force them directly through the winds, and you can also form them through wakes behind topographic features. But baroclinic instability is believed to be the main source of eddy energy, and there's two classic papers on this, Charney 48 and Eadie 49, although Eadie did the work first, and people like Eadie because it's easier to understand, essentially. And so what he did was just take a model with uniform rotation, uniform stratification, uniform shear, and if you're into potential vorticity, then opposing PV gradients at the upper and lower boundaries. So just a uniform shear. And you can then solve mathematically for the most unstable mode. I'd say it's a rather difficult exam question to do, but it's doable. And you find that the most unstable mode consists of eddies that tilt against the shear, and that's kind of important. If you want to extract energy from the mean flow, your eddies have to tilt against the shear. And you find that the growth rate for the most unstable mode is given by 0.6 F over N du dz. This is the energy growth rate. Normally you see 0.3, but it's double that for energy. So you get about 3 days in the atmosphere, which kind of fits with the timescale over which weather systems grow, and you get, a month in the ocean. So ocean eddies evolve more slowly. And the scale on which they develop is characterized by the deformation radius, the Rossby deformation radius, which is about 100 kilometers in the atmosphere and 50 kilometers in the ocean. So the Brunt-Weissala frequency came up earlier, I think, in someone's lecture. So, okay. Now, if we look at where eddy energy is in the ocean, so this is the RMS variability of sea surface height, a very old image, actually, from the early days of altimetry. And you can see that you have the highest eddy energies basically over the separated western boundary currents and over the circumpolar current. So where the flows are strongest, it kind of makes sense. And if you compare this figure, at least qualitatively, with the ED growth rate, so of course, you know, the stratification isn't uniform here, the shear isn't uniform, but nevertheless, you know, one of the things we do in physical sciences is we then sort of apply these ideas well beyond where you're allowed to apply them. And this is what you get for the ED growth rate. And at least qualitatively, there's a great match between where you find eddies in the ocean and where the ED growth rate is large. And then on the scale, well, this is a wonderful composite image showing cloud cover in the atmosphere and some, I guess, you could argue these are sub-mesoscale, I guess, eddies. But eddies off the coast of Alaska, you're looking at a chlorophyll proxy here. And you can see indeed that the ocean eddies are a much smaller scale than in the atmosphere. Okay, one of the questions that comes up a lot is why the deformation radius? It's quite hard, I think, to get your head around what the deformation radius is. And the way I like to think about this is to do two thought experiments. So the same experiment, but in different limits. So we're going to imagine you have a dense cylinder of water that's initially held up, and then you remove the barrier, and you ask what's going to happen. And we're going to do this first for length scales that are much shorter than the deformation scale. So what's going to happen if I remove that cylinder to the dense water? I think I saw the answer. It's going to spread out, right? So that's exactly what happens. The dense water will spread out, the light water will come in, and actually we were talking about rotating convection with the ice problem yesterday, so I was looking in my laptop for old images. Oh, sorry, first, the speed is given by the square root of reduced gravity times h square rooted. Just dimensionally, it has to be that if you think about the relevant parameters. I used to go to a summer school in Cambridge, and Herbert Huppert always used to bang home. You can often get most of the answer by just thinking about the dimensions of the relevant parameters. And that's the only combination, really, of the relevant parameters. So there's probably there's a 2 in it somewhere, I think, but, you know, that's a detail. So I was raiding my laptop looking for pictures, and here's a nice picture from the when we used to do fluid experiments at Reading, when I taught there, and showing one of these density currents spreading out. And that current is going to keep spreading out until it feels the effects of rotation. And the rotation timescale is about a day, or 1 over f. So basically, over a rotation period, the current is going to travel a distance, root g prime h, divided by f. And that is the Rossby deformation radius. So it's how far a dense anomaly spreads out until it feels the rotation, at which point it gets deflected by the Coriolis force and comes into thermal wind balance. And instead of spreading outwards, you then get a flow around this blob. So you kind of form an eddy, in effect. Now we can do the same experiment for length scales that are much larger than the deformation scale. So this is ice, or convection in the ocean, rotating convection, because the deformation scale is tiny next to Antarctica. What's going to happen in this case? You can't spread, well, you will spread out, but you'll spread out a minuscule little distance. So if this is 500 kilometers, I think it was, you mentioned yesterday, then maybe you spread out 10 kilometers or 5 kilometers, whatever the deformation scale is. And so what happens is you very quickly, oh gosh, I should look at what's coming up first. So the kinetic energy over the available potential energy scales as LD over L squared. So almost all of the energy inevitably is going to be in the form of potential energy. Or another way of putting this is it's really hard to convert that energy into kinetic energy. It's impossible, actually. So what you'll do is you'll almost instantly get a rim current through thermal wind balance around this dense blob. And we'll see what comes next. Oh, and then that rim current itself can go unstable. I'm not sure how it works in the presence of ice, because ice will probably damp any eddies, but if you're in open ocean, this is what you'd expect to happen. And the system, the dynamics will select the deformation scale to form the eddies because that's the scale at which you can convert potential to kinetic energy. You just can't do it at larger scales. And so sort of both of these experiments are sort of pointing towards the same scale, that you're inevitably going to end up with energy at the deformation radius. And this is a beautiful lab experiment. So you take a frozen disk of potassium permanganate in a rotating turntable, and you let the water sink, and basically what goes down is balanced by water upwelling in between, and very quickly you just end up with a mixed cylinder of dense water. And then if you look from above, can you just about see the eddies beginning to form there? So, and it's a great experiment to do because it's really robust, and you can change the rotation rate and change the number of eddies. And you get your hands to go brown, which you're not meant to do, but it happens, whatever gloves you wear. Whoa. Right, I'm giving up on my beamer. That's too scary. Oh well. We're moving on now to parametrization of eddies in models. Okay, my favorite slide. I've been showing this one for 20 years, and when I gave this talk in Bad Honnef, I had two audience members who were behaving very badly, Eric van Sebille and Helen Johnson, because turns out they were taking bets on how long I would take to show this slide. And it was Eric's fault, apparently, but yeah, I got him back in his talk. But anyway, so sea surface temperature in two ocean models. It's North Atlantic. I know it's Southern Ocean here, but it's I like this slide. So this is a climate resolution. It's one of the models we ran ourselves some years ago. It's not a movie. A movie would be pretty boring. You'd see the seasonal cycle. See a very diffuse Gulf Stream. And at 12th degree resolution, and I'm not sure where my degrees have gone, you can see that you've got a much narrower Gulf Stream, and everywhere you look, the system is eddying. So this is the MICOM model, a very famous simulation from the late 90s. And then this is reality. So this is a satellite image showing the sea surface temperatures. And you can see, again, at least superficially, there's a really nice agreement between the high resolution model and the low resolution model. Okay, I'm going to have to click here because I do not want to jump unintentionally. If you're doing a fluid dynamics course, the first thing you would do here is say, well, what's the Reynolds number? And the Reynolds number basically measures the ratio of advection to viscosity. And so when the Reynolds number is small, you have a viscous sort of laminar flow. And when the Reynolds number gets above about 1,000, the flow will go turbulent. So what is the Reynolds number in these models? Well, it's about 1, possibly up to 10 in a climate 1 degree model. So not surprising you have no eddies. At 12th degree resolution, it gets up to about 10 to the 3, maybe 10 to the 4. So we've undergone the transition to turbulence. These are easy numbers to estimate because you can just take something like the Gulf Stream transport and divide by the scale depth to get U times the length scale, and we know the viscosity the models run with. And in reality, the Reynolds number is about 10 to the 10, 10 to the 11 in the ocean. So, and although that may seem a long way away from 10 to the 3, and it is, fluid dynamically, I would argue that 10 to the 3 is closer to 10 to the 10 than 1. But, yeah. Why what? Simply because at coarse resolution you need to run with a bigger viscosity or you're numerically unstable. So the viscosity is what, 10 to the 4 or something here, and probably 10 here. Meter squared per second. Okay. The other question I like to ask the students, and again, Bad Honnef students and Andrew are banned from this, is if you could place your hand into these two models, but let's go with the 12th degree model, what would the water actually feel like in a 12th degree model? You're probably banned as well, Andrew. Student question. Any ideas? Yep. Okay, honey. Anyone else? No, I mean exactly like that. What kind of fluid, like honey? Or anyone think honey or any other ideas? Oh, you've heard. Yeah. That must have got out, because I spent too many hours one day Googling the viscosities of fluids. The answer is peanut butter. This beamer. It's a very strange peanut butter because it's a non-Newtonian peanut butter. It's stickier horizontally than it is vertically, but I'm pretty sure it would still feel like peanut butter. That was in response to Trevor McDougall's comment once. He complained about that. And God knows, I never found a fluid with the viscosity of a 1 degree model, but I think it's probably roof tar or something. So, as I always say on this slide, if you learn nothing else from the school, you now know that even peanut butter can be turbulent if you have a big enough basin. Smooth peanut butter, I should have said too, but non-Newtonian. Okay, another interesting question you can ask is, if we resolve the deformation scale in the atmosphere by the same number of grid points as we resolve eddies in the ocean, what would be the equivalent resolution to a 1 degree climate model in the atmosphere? And the answer is a 30-degree atmosphere model. And I don't need to ask you, would you trust the weather forecast made on that grid? So, and yes, it's a bit flippant. This goes back to Peter Kilworth, but it makes the point that, you know, the resolution is really coarse in a lot of these climate models. And yes, we have moved beyond 1 degree, but we're still not resolving the eddies very well. Okay, parametrizing. So we had this slide yesterday on Gentle McWilliams. And Gentle McWilliams had a brilliant idea. So prior to Gentle McWilliams, what was being done is that we were representing eddy fluxes of heat and salt just through a horizontal downgradient closure. And I was reminded in coffee that I never told you what an eddy closure is. It simply means a relation between an eddy flux and large-scale fields. So we used to say, for example, phi prime t prime was minus the horizontal gradient of temperature, and the same for salinity. And that was wrong because it introduces spurious sources of heat and salt into your model. So Gentle McWilliams had this brilliant idea that you want eddies to, the eddies, with eddy, a turbulent fluid in the ocean, fluid parcels are conserving their neutral density. And so you want your eddies to mix along the density surfaces, but as I said yesterday, that's not enough because mixing density along a density surface does nothing to the density field. And so what you need to do is introduce a circulation that acts to flatten the density surfaces. And this is really mimicking, or if you like, parametrizing baroclinic instability. And I didn't have the formula yesterday, but this is what's used. And it's basically that the horizontal eddy transport is d by dz of the slope of the density surfaces times diffusivity. And in fact, interestingly, buried in this is really a downgradient buoyancy flux, but it's implemented in a very clever way as an eddy-induced advection. And you can show that this guarantees that you will remove available mean potential energy. And then over the following sort of 20 years or so, I'd say most of what was done then was about relating this eddy diffusivity to the mean flow, or more recently to the eddy energy field, and that's the approach we're going to be taking here. Right, we talked yesterday about how these eddy-induced transports are real. So eddies don't just diffuse, they advect water masses, as we saw in this idealized experiment. I won't dwell on it now. And then I told you about the Dana Basaglu et al. Paper, and again yesterday I only showed you part of this, but Matt gave a nice lead in to what I'm going to show now. So I showed you how that the Deacon cell disappears when you include the effect of eddies. So this is much easier to reconcile with the observed water mass structure. But Matt also mentioned that they solved a lot of other problems at the same time. And this overturning cell, prior to Gentle McWilliams, really was real. I mean, it was supported by horizontal diffusion of heat and salt that was allowing this massive overturning, and so led to these really deep mix layers in the Southern Ocean that were completely spurious. So here is the distribution of deep convection in the new model, the old model prior to Gentile-McWilliams, and in the new model with Gentile-McWilliams. And you can see widespread deep convection over the Southern Ocean, which we know is not real. These are very, very deep mix layers. And in the when they included Gentile-McWilliams, maybe they got a little lucky to get it quite this good, but you know, you really got the convection in the Weddell Sea, Ross Sea, a little bit of intermediate water formation, Lab Sea, the Greenland Norwegian seas. What I took away from this paper, and this is in no means to do down Gentile-McWilliams, I think it was the brilliant contribution of the 90s, is that I think they made a lot of progress by basically removing something that was obviously wrong. And it makes it sound, you know, to underplay what they did. To the contrary, I think what we were doing was wrong, and they realized that, and that then opened the door to lots of future work. And it led to better models. And I really learned from that is if you think about the fundamental physics of, in this case, eddies preserving their densities fluid parcels conserving their density as they are fluxed around the ocean. By focusing on that and making sure that eddy parametrization didn't destroy that property, you got all these beautiful results suddenly appearing. Okay, so that was my sort of very brief introduction to what eddies are, why the deformation scale, and how we parameterize eddies in models. So I'm going to move on now to talk about more recent work that my own group's been involved with, what we call geometric, which I'll introduce shortly, and the idea of eddy saturation. So first I want to ask the question, well, why do we want to do this? And there are many reasons I could give you, but for the Southern Ocean, I think the easiest answer is that we know we have a systematic error in non-eddying ocean models, and this is the absence in those models of eddy saturation. So for many years I worked with a brilliant postdoc, student then postdoc, is now at Bath, Dave Munday. And he's been my go-to modeler, really, because if you want to do something really carefully and right, you go to Dave, because he will get it right, you know. I lost track of how many advection schemes he tried to get the diapycnal mixing down to, the spurious mixing down to acceptable levels. So it's not showing up great on these slides, but basically there's an ocean model here. The atmosphere is irrelevant. We basically blow a wind stress over this idealized basin. It's 20 degrees wide, 60 south to 60 north, and has a re-entrant Southern Ocean channel with a Drake Passage sill. And the reason we did this, we wanted an idealized model that was interhemispheric, that we could run repeatedly to equilibrium. And this was published in 2011, so they were done around sort of 2009, 2010, the experiments, and we were scavengers on the supercomputer at the time, and we burnt a lot of NOC's time actually that year because they had an underuse. So we only got up to 6th degree resolution, but all of these experiments had to be run mostly for over 1,000 years or so, because we wanted to go to equilibrium. And what we're plotting in this panel is the circumpolar volume transport, so the ACC transport, if you like. It could be global heat content, it would be pretty similar, against wind forcing as a multiple of our control value. And we went from 0 times to 5 times our control. And when you've got Gentile-McWilliams, what you expect to happen does happen, so stronger winds, stronger ACC. But when you do this at 6th degree resolution, so I'm going to call it eddy permitting, and call half degree wobble permitting, because it's not really eddies, it wobbles around a bit. What you can see at eddy permitting resolution is in this model there is no sensitivity at all of the transport to the wind stress. So how do we reconcile that with the textbook paradigm? I mean, it's just not right in this model. And as Matt said, yesterday, what actually happens in the model, so I put this back in after Matt's comment, this slide, this panel, is that as you increase the wind forcing, the eddy kinetic energy increases. In fact, almost linearly at 6th degree resolution. So the effect of winds is not to strengthen the current, it's to increase the eddy energy, which is kind of interesting. And so you might think, well, the eddy energy is going to affect the eddy diffusivity, and it's kind of correct, I think, that. So one way to think about this, but it doesn't really explain why the eddy energy increases, is that as you increase the winds, yes, you're putting more momentum in, but you're also damping the system faster through the eddy diffusivity increasing, and the two sort of cancel each other. Right, so in geometric, it was very much inspired by Jensen McWilliams, and I just moved to a physics department at the time, and physicists love talking about symmetries and conservation laws, and I do too. So we wanted a framework to try and parameterize and interpret, and I think actually this is the real reason I do this, is eddy mean flow interactions, where we try and keep as many of the underlying symmetries and conservation laws as we can. So I'm a big believer that the less you meddle with the Navier-Stokes equations, the more they can just sing and tell you what the answer is. So you want to intervene as little as you can. So this might look a little technical, and it is, but just to give you an idea of what we're doing, we have a momentum equation where we introduce an eddy forcing, and we write the eddy forcing as the divergence of a stress tensor. And basically it just says eddies can flux momentum vertically, so in the Southern Ocean they flux momentum down, but they can also flux momentum horizontally. And it's a tensor because you can flux all three components of the momentum in all three directions. But crucially, when the eddies remove energy from the mean flow, we then put it into a new equation for the unresolved eddy energy. So we have a new equation, ddt of eddy energy, given by all sorts of divergence of all sorts of fluxes, plus a source of eddy energy, which is equal and opposite to the sink of mean kinetic energy. And what got me excited is when we realized that the size of this eddy tensor is set by the eddy energy. So in fact, you can show that if you take all the entries of E and square them and add them together, then they are bounded by the eddy energy squared. And this is important because it means that all your remaining unknowns are dimensionless numbers, and it turns out they're less than 1 in magnitude. So, if you know the eddy energy, you should not be prescribing an eddy diffusivity, because then you're over-intervening, because you don't need to parameterize anything other than non-dimensional numbers. And what do those numbers represent? I have to stop using that beamer, it's annoying me. They basically measured the tilt of the eddies. Do the eddies have a preferred direction? And if they do, what is that direction? And so we already looked at eddies tilting in the vertical, but they can also tilt horizontally. And here's a nice example of a jet where the eddies are tilting with the jet, with the shear. So they sometimes get called banana-shaped eddies or boomerang-shaped eddies. And just by looking at that shape, I can tell you that that will be accelerating the flow. They're fluxing momentum into the core. And Stephanie Waterman, in her thesis, produced a wonderful picture in the Kuroshio from observations, showing that initially the eddies, after the Kuroshio separates, are actually decelerating the Kuroshio, so they're growing. But then further downstream, the tilt suddenly flips around, and they sharpen up the Kuroshio again. So you can measure these quantities observationally. And perhaps the nicest example is on the giant planets, because you can just look at the clouds of Jupiter and see some of these tilts. And just from those tilts, you can tell which way the momentum is being fluxed. So that's an aside, but... Right, so in the Southern Ocean, it's the eddy form stress we really care about. So it's how we get the momentum down from the surface to the bottom through this eddy form stress we talked about yesterday. And we're just going to use the mathematical identity that form stress is, well, if you keep track of all the parameters, it turns out to be a non-dimensional alpha that's less than 1, F over n, so Coriolis over buoyancy frequency, times the eddy energy, which we're going to solve for. And our parameterization is to set alpha. So in an ocean model, we set it to 0.05, but that is the parameterization, is setting alpha. This is a mathematical identity, except that we don't know the value of alpha. It's less than 1. Now, I'm also a pragmatist, and ocean models are all written to use Gentleman-Williams, but what you can do is reverse engineer this into Gentleman-Williams and ask, well, if we made it look like Gentleman-Williams, what would the Gentleman-Williams diffusivity need to be? And the answer is, it's alpha, our non-dimensional number, times the buoyancy frequency, times the eddy energy, divided by the horizontal buoyancy gradient. And this really worried me, because normally it's kappa times that gradient that we want. And, well, we're dividing by the gradient. But then I realized the dipycnal mixing community have been doing this for years with a sort of n squared on the bottom. So I think it's fine. Okay. So just again, if the eddy energy is known, the only freedom is to specify alpha. So we're going to implement this in Gentleman-Williams by solving an energy budget, keeping track of the eddy energy, and then we're going to specify alpha and see what we get. Okay, so I've got just 3 proofs of concept of this. The first is an analytic solution we're going to test against. So the ED growth rate is an analytic solution. It's a textbook problem. And so it's a great playground, if you like, to sort of test out this approach. Does it work? And it's a really, there's so much symmetry in the ED problem that it just works beautifully. That you can show that the eddy energy integrated over the domain grows at a rate alpha F over n times the shear. And that is the ED growth rate if alpha is 0.6. So again, we've not put this into the parameterization. We've left enough dynamics in the Navier-Stokes equations for it to still know that that's the right answer. The only bit we don't know is what alpha is. So in this case, it would need to be 0.6. Now, the real world is not linear. So if you want to go to the nonlinear ED problem, you need to go to numerics. And Scott Bachman had just written a beautiful paper for his thesis on the ED problem. And so I wrote to Scott and asked if he could check our parameterization geometric out in his model. So he has a channel. This is a baroclinic front, and it's quite clever what Scott does. By letting it slump slowly, he samples a lot of different diffusivities, and then he basically drops a dye into the model, a tracer, and measures eddy fluxes. And we're going to compare the predicted eddy diffusivity from geometric against the diagnosed eddy diffusivity from the model. And this is what you get over 4 orders of magnitude. For a turbulence closure, this is really good. So the dashed line is with alpha equals 0.2, which works well for the sort of diffusivities we get in the open Southern Ocean. There's an offset at low values because we know for the linear problem alpha is 0.6, so alpha does vary a little bit. But every other closure we looked at had huge scatter when we did the same comparison. But then the thing that really got us excited was we realized that it also gives you eddy saturation. So I showed you Dave Monday's experiments, and this is what happens if we parameterize this problem with geometric, so the red line here. So green is the eddying solution, and red is the solution with the geometric parameterization. And we basically get, to good approximation at least, no sensitivity of the circumpolar volume transport to the wind stress. And even if you have 0 winds, you've still got a big circumpolar current. And so this is where I love theory, because suddenly you've got a simple model and you can say, well, why is this happening? And so we went through pages and pages, literally, chapters and chapters of algebra trying to figure this out. And It's kind of depressing at the end. You can get it down to 3 equations, but you know, that's how you get there. You try lots of things. So let's remind ourselves again of our view of the Southern Ocean, our simple conceptual model. We got the wind stress at the surface, balanced by an eddy form stress, and we want to get the momentum down through a bottom form stress, and we need to get it down through this eddy form stress. So in equilibrium, all 3 of these should be equal. And so the first thing we're going to do is write down the momentum budget, which is that the wind stress must balance the eddy form stress. If you remember to yesterday, this is what Johnson and Bryden assumed. If you want to take it to the next level, you add a Coriolis force from overturning. But it's a detail, I think. Now, in geometric, the eddy form stress is set by the eddy energy. So that is basically the eddy energy. So times F over N. I'm doing that physics thing of ignoring all the constants here, but that's basically the eddy energy. And so look, it's kind of interesting. The momentum budget says the wind stress sets the eddy energy, which is exactly what we find numerically. So we'll park that below. And then we want an eddy energy budget. So in equilibrium, the source of eddy energy must balance the sink. Otherwise, the eddy energy is going to disappear or grow. The source is the ED growth rate times the eddy energy. So basically, the shear times the eddy energy. And the sink, we're just going to cheat here, actually, and write it as eddy energy over a damping timescale. So all the physics is lurking in that timescale. And then the eddy energy cancels out, and what you find is that the shear is set by the damping timescale. In this model, it will be bottom friction. And if you integrate twice again, you find that the circumpolar transport, at least the thermal wind part, is basically set by 1 over the damping timescale, so the friction. And in fact, it's really weird because the larger the friction, the stronger the current. So it's kind of anti-frictional. So that's weird, isn't it? I increase the friction, I get a stronger current. And why is that? Well, because friction doesn't appear in the momentum budget. It's irrelevant. Form stress is so good at removing momentum. The main effect of friction is to damp eddies. And if I take the eddies away, the current will spin up. It has to get faster to overcome the damping effect of friction for the eddy energy to come back. So I didn't believe that result, so I went back to Dave Munday, my favorite ocean model, and I said, Dave, can you try this out? And so this is a higher resolution 10th degree channel with a ridge in the middle. And sure enough, as you increase the bottom drag, and I hate these units, I can't remember why they're in those units, but anyway, you increase the bottom drag for any wind stress except 0, which was an outlier here. Basically, you find that it's the bottom friction setting the ACC transport, and the stronger the drag, the stronger the current. So I wanted to call the paper an anti-frictional model of the ACC, but my co-authors objected because it's not really true. So we've put this into NEMO. It's also in MIT, and I think it's in MOM, from the last I heard. The main thing you need to do, apart from hacking Jensen McWilliams to just change the diffusivity, is you need to add an eddy energy budget. And it's kind of all the things you'd expect. So you have a source of eddy energy given to you by geometric. We have westward propagation by Rossby waves, and we also advect by the depth mean flow, which empirically at least seems to do the right thing. We diffuse eddy energy, because if you had a lot of eddy energy in a little blob, well, eddies will spread out somewhat, so this is very ad hoc. And then we damp the eddy energy with a timescale that we just prescribe, typically to be about 4 months or so, and I'll say why in a moment. So what just appeared there? I don't know. So this was the eddy energy from a 12th degree version of the model, and with 1 degree resolution. It's certainly not perfect, but you're getting the hot spots in the right place. We do badly where the eddy energy is weak, and I think this damping timescale needs to be non-linear, but we really didn't want to sort of be accused of over-engineering it at this point. And I'm just going to show you really one result from the model, which is that this eddy damping timescale, it turns out, sets just about everything in the equilibrated global circulation. So here is the ACC transport from 165 sverdrups down to 100 sverdrups as a function of eddy damping timescale in days. So we're changing that damping timescale from 60 days to 160 days. But even the AMOC is varied by a sort of 50% if you change the Southern Ocean eddy energy damping timescale. And you change heat content by an amount that's an order of magnitude larger than the anthropogenic heat uptake to date. In fact, I've got a map of the change in heat content between 160 days. Well, when you reduce the eddy damping to 160 days, and the other way around, isn't it? Increase it to 160 days or reduce it to 60 days. And you can see that this Southern Ocean eddy parameter is affecting the global stratification, and that's why it's changing everything in the model. And yet I think it's a parameter people are not really thinking about at the moment. I have no idea if it would change would have changed in the past. I can't think of a reason why it would, but who knows. I also think this offers an explanation for this this result that was summarized really nicely in a paper by Andreas Klocker. Was this last year, I think now, about deep-reaching global overturning generated by surface buoyancy forcing. And I think this basically provides an explanation for that. So I've been trying to come up with this analogy for a while. I've used it in talks, but in a descriptive way. But I started yesterday drawing this analogy out, and it's better than I thought, actually. So this is my sort of thought experiment for eddy saturation in the ACC. So we're going to think about baths, two baths, one with the tap turned fully on and one with a dripping tap. And my question to you is, what's the equilibrium water level in those baths? It's obvious, isn't it? This is very real for me at the moment. We've got a dripping tap at home and I need to get the plumber in. So at the moment we have a little container and we have to empty it every week. I really should just call the plumber in. But the truth is that both of these, sooner or later, as Matt said, if you wait long enough, a small source will fill up your bath. And I'm not sure how well this has come out, but can you see the overflow here and the dripping overflow here? Now, this analogy is better than I thought it was. The tap is basically the wind stress, and the ACC transport is the height of the water in the bath. So when I change the wind stress, I'm not changing the height of the equilibrium height of the water in the bath. But what I am changing is the rate at which water's overflowing, which is the eddy form stress, or proportional to the eddy energy. So the effect, when I change turn the tap on faster, I increase the eddy energy, but not the transport. I must work out the equations for this. I reckon that may even be close. And then what does friction do in this model? So this is where I'm beginning to push things a bit. The effect of increasing friction is basically to raise the walls of the bath so that you end up with a stronger ACC. So that's probably the weak point of this analogy. But so I don't know if that works. I would love to know. I'm sort of dry running that in real time in this school. But that's my analogy for the ACC. I'll just say quickly that the time-dependent version of this model is also fun. So it's a two-dimensional dynamical system. So you just add the DDTs on the right-hand side for transport and eddy energy. And you can do all sorts of fun maths, sort of Hamiltonian mechanics, which I teach in Oxford, so I've been enjoying trying to find applications of it. You basically get a damped oscillator, which you can excite stochastically, and it's actually identical model to the one Ellie Ong had, the paper you're with, and also Martin Ambam and Lincoln Novak for the storm track. So That's kind of fun. And then finally, rethinking ACC dynamics. I'll go quickly through this. So I said yesterday that I really think we need to rethink the textbook paradigm, because in the models, and I know it's not observations, but it's the best we can do here really, when you change the wind stress, you don't find a big change in most models of the ACC transport to wind stress. Some models do show sensitivity, but certainly very reduced. If we repeat the analysis I just showed you, but we do it more carefully, assuming an exponential stratification, then you can derive a formula for the ACC transport that looks like this. So it's 1 over the eddy damping timescale times pi. You can blame Dudley-Chelton for pi, times the deformation radius. So Dudley defines the deformation radius with a pi in it, so there's a pi in our formula, times the width of the ACC, times the E folding depth, divided by alpha, our eddy efficiency parameter. So those are all the parameters. We can estimate them all basically by, I think I'm going to whiz over this, but you look at the momentum budgets and you know most of the parameters, so you can figure out what alpha is. So alpha comes out to be 0.05. And the eddy energy damping timescale, my former postdoc Xiaoming Tsai had a great idea here of, you don't really know the sink, but what you do know is the source of eddy energy from the wind work. It has to end up in eddy energy sooner or later. And you know how much eddy energy is in the ocean with a big error bar. And then if you average over, I know it's ridiculous, 30-degree bands, because these are noisy numbers otherwise, you sort of get a sense that that timescale in the Southern Ocean is a few months or so. And so putting it all together, this formula doesn't look like it should work, because I'd never seen an ACC transport formula like that, but so what do we do first? The deformation scale from Dudley-Chelton is 20 kilometers. Width for the ACC we got as 10 to the 6, 10 to the 3 for the E folding depth. Alpha we estimated just now to be 0.05. We've estimated T eddy to be 10 to the 7 seconds, and the one number we actually know here is pi, which is 3. So 3 times 2 is 6, divided by 5, that's 1 at the level of this. This is scale analysis. But amazingly out, you get sort of 10 to the 8 meters cubed a second, 100 Sverdrups. So I wouldn't want to claim more than an order of magnitude here, but I was kind of surprised that that gave us the right ballpark. So I don't know. There are different ways to write the formula, and buoyancy forcing is certainly lurking in here through the deformation scale. Maybe wind stress is implicit in some of this too, but to leading order, I'd say it's not the usual formula, saying ACC transport goes with wind stress. Okay, so I'm going to wrap up there. So the ocean's populated by an intense mesoscale eddy field. I'm going to argue that equilibrated ocean models will not routinely resolve geostrophic eddies for the foreseeable future. This is a controversial statement because a lot of people are now saying, oh, we can resolve eddies, but the problem is no one runs their models for 3,000 years to equilibrate. And certainly if you're doing paleo, you need to do that, and you want to do multiple sensitivity studies. So I think development of parameterizations is still a practical necessity, but probably more important, it's useful for advancing our understanding. So I think the recent advances have pushed forward our understanding, but I want to add there's a lot left to do, especially with the sub-mesoscale. This is the turbulence problem. It's one of the toughest problems in physics, and we're really just scratching the surface here. But there are easier, this is one of the Clay Millennium Prizes where you can win $1 million if you solve the turbulence problem, but I would spend your energies trying to solve something else if you want to earn one of those prizes, because I don't think this is the easy one. Okay, thank you.